Any questions on that? No? Okay, here's a generalization of the previous result. So this one says that the probability of A union B union C is the same as the probability of A plus the probability of B plus probability of C minus probability of A intersect B minus the probability of B intersect C minus the probability of C intersect A plus the probability of A intersect B intersect C. In other words, the probability of A union B union C is the same as the following. First, you add up the probabilities of one-way intersections, which are P of A, P of B, and P of C, and then you subtract probabilities of two-way intersections, and then you add the probabilities of three-way intersections, and so on. Okay? So in this case, because I have only three sets, I stop at the last term is the probability of three-way intersection. Is that making sense? So again, the reason the equation is like this is because, first of all, on the right hand side, by writing P of A, P of B, by adding P of A, P of B, and P of C, you have double counted the intersection of A and B. You have double counted two-way intersections. So that's why you're subtracting the probabilities of two-way intersections. But by the time you subtract out the probabilities of two-way intersections, you have subtracted out the probabilities of three-way intersections too many times. One too many times, one extra time. So that's why you're adding back in the probabilities of three-way intersections. If I have more sets, I'll be doing more. Is that making sense? You can also prove this by using the previous case with two events, right? And I can use that also to prove this, but I won't bother doing that. This is similar to the this is like the this is also known as the inclusion-exclusion principle. Previously, we have looked at that solely in terms of the number of elements of the sets. Here, we are looking at it in terms of probabilities. And so, like I said, you can generalize that. So this is a general proposition that if I have n events, A1, A2, an, what's the probability of the union of A1, A2 up to an? Well, again, what you do, you start with adding the probabilities of one-way intersections. One-way intersection means you have the probabilities of the individual events, and then you subtract the probabilities of two-way intersections, then you add the probabilities of three-way intersections, then you subtract the probabilities of four-way intersections, and then you add, and you keep doing that until you get the probability. The last term would be the probability of all the events. Probability of the intersection of all the given events. Yeah, it's A1 up to an. And notice that the sign of the last term would be -1 to the n plus 1. -1 to the n plus 1 would be the sign of the last term. Any questions, anybody? Now this shouldn't be surprising because you already have seen the inclusion-exclusion principle for counting the number of elements in the union. Okay, so one thing that I want to point out here is that the probability of the union of events AIs where where the I could be from 1 up to n. If there are only finitely many, it could be 1 up to infinity as well. And the probability of that is smaller than the sum of the probabilities of the individual events. So the probability of the union of AI is less than the sum of the probabilities of the AIs. Is that making sense?